Well, greetings everybody. I'd like to show you how to solve this question, which I'm finding right now on my math lab. I'm given a function that measures the population growth over time, and I don't have a formula for that function, but I have some data points. And that's often the case. It can be difficult to derive actual formulas that track something like population growth because such a thing can be unpredictable and has many factors that influence it. But nonetheless, I have this data. I have the population at various times, and that's all this function would measure anyway. Okay. Uh, I also see that on this graph over here, the units are converted a little bit. The population is in measurements of thousands, so that 400 right there means 400,000. Okay. Now, so let's look at part A. It says compute the average rate of growth of the city population from 1970 to 1980. And then the next part, explain why the average rate of growth calculated in part A is a good estimate to the instantaneous rate of growth. So let's talk about some background and concepts before we talk about the solutions. So I see the situation like this. I've got this function that measures population over time. It's called P of t. I might also refer to that as the curve, okay, when I look at the graph. The reason is that what we're talking about right now is somewhat geometric, meaning that I talk about the curve, I talk about secant lines and tangent lines with respect to that curve. So I think curve can be a better term than function when we're talking about it like this. I'm given these 2 points on that curve, and I'll explain why I have the numbers the way they are as opposed to the way they are on the graph. Okay, so I'd say like, well, in 1970 I got the population 258 296, and in 1980 I get the population 499 749. Okay, so you see the curve in black, the secant line through those 2 points in red, and then the tangent line in blue. Okay, so to use the terminology in the question for what is the average rate of growth or what is the instantaneous rate of growth, the slope of the secant line is the average rate of change, or in this case the average rate of growth, and the slope of the tangent line is the instantaneous rate of change, or in this question the instantaneous rate of growth. Okay, so now that gives me a way to calculate what I need, because in part A, if it says what's the average rate of growth, well, I know that that's the slope of the secant line between these points. Now additionally, I noticed that there's some units specified, people per year. So I included my points as 258,296, for example, as opposed to the way they are over here, because these units are in thousands of people, not in people. Okay, so I'm going to calculate and make sure that I get units of people per year. Now, if I, as a result, take this y coordinate, 499,749 people, minus this y coordinate, 258,296 people, and I'll get units of people just like it wants. And then if I take 1980 minus 1970, then I'll get 10 years. I'll get units of years just like we're supposed to. So anybody that's doing science or engineering or any kind of measurement heavy discipline, we're going to have to pay attention to units as we go further and further. So this would give me the slope of the secant line and in the units that I need for this question. Okay, so I continue breaking this down and I get 24,145.3 people per year. So that's the average rate of growth from 1970 to 1980. On average, we're growing by about 24,000 people per year. Okay, so that's our answer for part A, the average rate of growth, just the slope of the secant line. Now in part B, I'll think a little bit more conceptually. It says explain why the average rate of growth calculated in part A is a good estimate to the instantaneous rate of growth of the city in 1995 or 1975. So let's see, 1975, that would be like somewhere in here, right in the middle of 1970 and 1980. And so the question appears to be asking, why is the slope of the secant line pretty close to the slope of the tangent line? Okay? That's the way I would understand it. Based on what I've told you as far as definitions of average rate of change or average rate of growth and instantaneous rate of growth, we're saying, why is the slope of the secant line a good estimate of the slope of the tangent line at 1975? Okay, so, well, just by nature of graphs, if my points are sufficiently close, then yeah, the secant line is roughly parallel to the tangent line, having roughly the same slope. Now, if you thought, hey, well, in this question, the way I've drawn this, they don't look close to me. Well, all I have to do is move this point over there. I can move this point close enough to that one, and they will be, for purposes of estimation, close together, right, in terms of their slope. Okay? Can you imagine that as this line approaches that line, and the secant line tracks with the points, the secant line and the tangent line are just going to merge together. So yeah, one can be a good estimate of the other. It depends on several factors, such as how extreme the curvature of the graph is and how close these points are. But okay, so I can give it to you in this case that yes, the secant line has its slope very close to the tangent line. Okay? And that's even if you plotted the tangent line at 1975, right? And you can see that, sure, the point in the vicinity, the same thing is going to be true. Okay, so that's why. Now, I report my answer of all these as the slope of the tangent line at t equals 25. That corresponds to 1975, okay? Is approximately equal to the slope of the secant line through those points that I used, okay? Yeah, we can see that that would be true if you use your imagination in the way that I encourage you to. Just imagine the tangent line to the curve in this vicinity. If you want to put it at 1975, put it at 1975. Put these points near that one. Put them close enough together. And yeah, the secant line and tangent line are going to have roughly the same slope.